Okay, so we will be doing the neural networks and the simplest form of neural networks here in terms of logistic regression. And logistic regression is nothing but a classification problem. So if you have something like email is a spam or not a spam, it's a classification problem. Then there is something in medical field, like if it's malign cancer or benign cancer. So all these are the classification kinds of problem, and logistic regression is used to classify these kinds of data sets. Now, this Excel sheet in terms of today's video, we'll try to only use Excel sheet and we'll not do any coding because we want to understand what is happening under the hood. And I think Excel sheet gives you that kind of layout to see the different moving elements of a neural network. And it's also good to make something from scratch in Excel sheet where everyone is well aware of. So we just focus on the maths and not the coding aspect of it in this video. So before starting anything, I think I'll just create a data set here, and the two things which I'll create is a simple one X feature, which right now I'm just giving it very simple that anything which is less than 4 is classified as 0 and anything above 4 is 1. So that's keeping it very simple and trying to focus on the maths part. Then we go into the y variable. So as mentioned, anything which is less than 4 will be 0 and anything above 5 or 4 is 1. So that's our data set for understanding the neural network as well as simplest form of neural network, which is logistic regression. Now we have to understand something here that what happens in a neural network. So let's say we have one feature and then we normally create a neuron which will have the same dimension as the input feature. So here it's input features and here it is neuron, right? So in logistic regression, we have only one neuron size. So the set x1, if we have only one input features, then there will be only one uh, this thing weights, which is W1. And then we will have a bias, again B1, which is for per neuron size. Similarly, if we have, let's say, two features in R, then there will be another set of weight here to multiply this with, and then we will just have one bias for this neuron. Right, so that is how the construction of neuron or perceptron is. So depending upon the number of features, here we have just used one feature, so we will just have one W and one B. So we can initiate it with just one and one. And the first thing we calculate is the Z value, which is nothing but a linear regression value. So we multiply our weights and we use the function F4 to lock it so that it doesn't change when we are changing the rows. So that's W1 into X1 plus the bias, which is set for 1. That's the complete formula here. And then we drag this and we get the Z values. Now, to create a logistic regression function, we also use an activation function, which is nothing but a sigmoid function. Now, the sigmoid function is basically squishing this Z values into in between 0 and 1. So the higher the Z values, so more it will be close to 1, and then the more negative values it is more close to 0. So the way we write is 1 upon Just I want to refer to this formula of sigmoid. It's 1 upon 1 plus exponential of the scalar quantity z. So I think I had it written it somewhere and I can directly copy it. So what it's doing is it's taking this z value in this formula and then squishing this z value into in between 0 and 1. So you can see it's positive value, so it's showing 0.88, which is close to 1. And for all these higher z values, it is almost 1. So it can't go more than 1. That's the utility of this sigmoid function, which we are using in logistic regression. And then thereafter, we can see our loss, what is our error. So in terms of error also in logistic regression, we use this formula, which is nothing but didn't copy. So what I'm trying to do is I'm just copying it from another sheet of mine where I had written this and need to remove this. This is kind of a tech trouble here. So what I'll do is I'll just try it once more. Yep, this worked. So what's doing is it's subtracting, or it's negative of y value, which is our original target values, and then log of the predicted values here. This is 1, and then negative of 1 minus y multiplied by log of 1 minus a, which is the predicted value. So that's the formula. So you can see for this, wherever we have correctly identified the loss is 0. And wherever we have not correctly identified, the loss is in positive value. So we need to optimize this weights and biases so that even these values which are not correctly predicted, they get predicted correctly. So our cost function, which is nothing but summation of all our error, basically it's an average of all our error. We can use auto sum or average. Yep. So that's the formula. Uh, it's saying right now we have 0.69 as the error in our model, and the way to actually reduce this error is to move these values W and B. You can keep trying and keep implementing different values and see how much of error comes, but this is not how the deep learning works. The deep learning works basically by automating this process of iterating over which W or which B value will give the lowest cost. So hence this forward propagation till here is done. This is one part of the deep neural network that you need to do a forward propagation of your model, basically using these initiated random variables in the beginning. And then looking at the cost function, we try to do a backward propagation of changing this W and B. So the first step will be, and now this is a little bit tricky. This is calculus part, so I'm not a expert in maths, but what I do is I understand that this is trying to understand the change in the input variables, and of that change, how much uh, gets affected into the output variable. So it's basically trying to calculate the slope of each function here. So we have used multiple functions here. And then we want to understand that sensitivity of each function and then propagate it backwards. So that's the first step. So dA, which means derivative of this loss function with respect to this activation function, and that we need to calculate. Then we also need to calculate dz, and we need to calculate x dz. Now, what dA is and what dz is and what x dz is, it's nothing but derivative of each function. First, I'll try to calculate. It's not allowing me to paste the values. I just wanted the formulas, but I think the formulas have gone. Okay. So I think I'll have to write it again, and let me try it once more. Yes, I've been able to copy the formula. So the formula is this y actual target label divided by the predicted label, and 1 minus again y upon 1 minus a, which is the predicted label. So that's the formula for calculating the derivative of activation function. Now, people who are good in maths, they can solve it and still arrive at the same value. So yeah. So we have calculated dA. Now we need to calculate the dz. The reason why I'm going from dA to dz is because it's chain rule. And in calculus, if you want to calculate dz, you need to first calculate dA. And if the formula of dz comes out to be simply a minus y, but you still need to calculate dA. Even though this formula I've written down, this looks very simple that you don't need to calculate dA, but to arrive at dz, at least from the calculus standpoint of view, you need to first calculate this, and then again you need to find derivative of this with respect to uh, the z. So that's the formula for dz. And then finally, we multiply these dz values with the x to get x dz's. Now, x dz's are nothing but they are what we will be using for our gradients updation purpose. So, yep, that's the dw we have calculated just now. And so this w will get updated with negative 0.236, and that's taking a step uh, downwards in the gradient descent. I'll just show that case as well as to what do I mean by updating this gradient descent. And then dv is, it's the summation of all the dz's and then divided by the number of training examples. So that's my dv. I think I'll need to put it here. So this is in total what we do. We forward propagate, we find out what is the error, then we do a backward propagation to see how much of W or B to be updated. So currently it says to reduce W by negative 0.23 and increase B by 0.18. So that is how the deep learning or neural networks will work, by taking these inputs from the layers itself and updating the parameters uh, by using this derivative side. Right, so I'll try to also show you what I mean by this updation of uh, weights and biases. So I'll just put some values here. Uh, So these are my weights. I'll just name it here. Yeah. And here I'll put all the biases values. So for different weights and different biases, we will try to see the slope of the derivative function. So it's all the way till some numbers because we need to find that slope. What I'll do is I'll use something which is called as what if analysis to uncover the different J values for different W and B values. My input cell will be this W and my column input cells will be B, H2, and then I get different J values in this what if analysis. Yeah. I'll just pick one here and insert a graph. So we'll come to know for different W and different B's, uh, what is the J value showing. Yeah. So this is currently going a slope and there is, we're not able to see the full complex convex version of this function, but let me try this one. Yeah. So this is much better. So for W0, we see it starts and B value -6, it starts at 1.44. So this is the, if we just update here the value 0 and -6, we'll get 1.45, which is almost same here. It's just rounded up. So it starts at this and then it's saying to update these values again here. So what will happen is once, like let's say for W0, and which is this value, we are trying to find the slope. And then this slope is nothing but dW and dB for each of the weights and biases. And then we are trying to update these numbers and then go to the next J value. So if we just have take one weight that is 0, we can see that it will slowly progress downwards. The weights will be negative till this point, and then this is where you will get the lowest value of cost function. And then if you have started the weights from here, which is somewhere around +9 instead of -6, so you'll see that the dw becomes positive. So in you will subtract this value from the w instead of adding it up. So that's how the slope changes from whichever side you have initiated, either -6 or 9. You get different dw values, and it's that's how the cost function gets converged by using derivatives. Now you probably understand why this backward propagation is needed. So we calculate the slope of this function with respect to w and b, and this is what the value we get. But to do that, we need to first calculate dA, dz, and xdz. So that's the complicated maths calculus part. If you want to get into it, probably you can, get into that. But it's better that if you are not a maths major, then you just stick to these formulas and then understand the concept. So that's a simple concept of the slope and the weights. right? I hope you like this lecture of deep learning under the hood, trying to uncover what exactly happens when you are initiating variables, biases, calculating the complicated backward propagated variables like dA, dZ, and then updating this dW and dB to your WNB. So what will happen is you will have to update this after this new W and new B, and then keep on iterating this process till this J is optimized with the minimum cost. So that's the optimization part. I'm just putting in formulas for new W and new B. Right. So when the slope is positive, it gets subtracted. When the slope is negative, it gets added. That's how I understand this W and B. Okay, so we can either do a simulation of how we conclude this J to the minimum, which is probably coming at 1 and minus 4. So we can keep taking this values inputs from here. Uh, minus 1.1, and then the slope is 8.72. So you get 1.4. It has reduced. Now you further carry on minus 1.2, 1.3. This is 9.51. Still get around that value, but uh, this gradient descent is nothing. It's not a 2D figure. It's a 3D figure. So it's a kind of like a bowl figure where slowly the steepest uh, slope it will take to lower this J. So that's how in coding it is more efficient in terms of Excel sheet. We'll keep doing it. It will take a day or more. But I think for one variable, if we see just one and we try to initiate it at 9 and then keep moving the bias by 1. So here the bias is zero point 0.4. Again, the new bias is 8.56. So we just move it to 8. Yeah, it's now 7.56 and cost has also come down. Now we move it to 7. The cost is 1.83. We move it to 6. Cost is 1.64. Move it to 5. Then 4. We can see slowly the cost is coming lower and lower. And at one point, the cost will become 0. So at 1 and 1, we are having 0.69 as the value. But we seem to still not have a good prediction of our variables. So let's see if we go down to minus 1. Yes, it has further reduced, and then it has also shown a good accuracy in terms of uh, predicting this, because if we want to put a threshold value here of prediction, like anything which is above 0.5, it's 1, and if anything is less than zero point 0.5, it's 0. That is how the sigmoid function threshold value is used, 0.5. So you can see that it has predicted 1 at least, and you can also put this in terms of label. I just want to put y and want to check it against that is there, and then I want to check against my predictions. So 1 is predicted quite okay. Then if I go to minus 2, the cost has further come down. Minus 3, it's 1, and now it's perfectly aligned to our initial data set. So it's 100% accurate, and the cost is also almost 0. So this is the overall picture. I hope you like this video, and I would like to further make such under the hood videos to make me and the audience understand what deep learning is. And it's a very simple thing. It's nothing much complicated. It's just a lot of functions, lot of activation, lot of weights and biases which are fine tuning this model. But under the hood, it's plain and simple. And I hope people don't get discouraged by this hard vector matrix coding, but understanding this concept and then making it useful for analytics purpose and obviously machine learning. Okay, that's all. Thank you.